One step at a time. The method of mathematical induction. Weak induction. Let us assume it is almost midnight and it has not rained all day today. If from the fact that it does not rain on a given day, it followed that it will not rain the following day, it will then also follow that it will never rain again. Indeed, from the fact that it does not rain today, it will follow that it will not rain tomorrow, from which it will follow that it will not rain the day after tomorrow, and so on. This simple logic leads to another very powerful tool in mathematics, the method of mathematical induction. We can try to apply this method anytime we need to prove a statement for all natural numbers m. Our method then has two steps. One, the initial step. Prove that the statement is true for the smallest value of m for which it is defined, usually 0 or 1. 2. The induction step. Prove that from the fact that the statement is true for n, the induction hypothesis, it follows that the statement is also true for n plus 1. If we can complete both of these steps, then we will have proved our statement for all natural values of m. Indeed, suppose not, that is, that we have completed the two steps described above. But still there are some positive integers for which our statement is not true. Let m plus 1 be the smallest such integer. Then m plus 1 is not the smallest integer for which our statement is defined, for that would contradict the fact that we completed the initial step. So our statement is defined and therefore true for m as m plus 1 was the smallest integer for which it was false. So our statement is true for m, but false for m plus 1, which contradicts the fact that we completed the induction step. Indeed, choose m equals to n in the induction step yields this contradiction. Having seen that the method of mathematical induction is a valid one, let us survey some of its applications. Example 2.1. For all positive integers n, 1 squared plus 2 squared and so on plus m squared equals to m times m plus 1 times 2m plus 1 divided by 6. Without the method of a mathematical induction, we could be in trouble here. The left-hand side is a sum that is not an arithmetic series or a geometric series, so we could not use the Nona formulae for those series. Moreover, the right-hand side looks slightly counterintuitive. For example, it is not clear how the number 6 will show up in the denominator. The method of a mathematical induction, however, solves this problem effortlessly, as we will see below. Solution 1. The initial step. If m equals to 1, then the left-hand side is 1, and so is the right-hand side. So the statement is true. 2. The induction step. Now assume equation 2.1 is true for n and prove it for n plus 1. The statement for n plus 1 can be obtained from 2.1 by replacing n by n plus 1 and is as follows. 1 squared plus 2 squared and so on plus n squared plus n plus 1 squared equals to n plus 1 times n plus 2 times 2n plus 3, then divided by 6. To prove a 2.2 from 2.1, note that these two equations look pretty much alike. In fact, their difference is a rather simple equation. We are going to prove that this difference is an equation that is, in fact, an identity. This is true as the difference of the two left-hand sides is clearly n plus 1 squared, while that of the two right-hand sides is n plus 1 times the difference between the product of n plus 2 and the 2n plus 1 minus the product of n and 2n plus 1. Then multiply by n plus 1 divided by 6 equals to n plus 1 squared. Therefore, adding the true statements 1 squared plus 2 squared and so on plus n squared equals to n times n plus 1 times 2n plus 1 divided by 6. And n plus 1 squared equals to n plus 1 times the difference between the product of n plus 2 and 2n plus 3 minus the product of n and 2n plus 1, then divided by 6. We get that 1 squared plus 2 squared and so on plus n plus 1 squared is equals to n plus 1 times n plus 2 times 2n plus 3 divided by 6. Therefore, the statement holds for all positive integers m. The previous example shows the one serious advantage and one serious disadvantage of the method of mathematical induction. The advantage is that instead of having to prove a general statement, we only have to prove two specific statements. That is, first we have to complete the initial step, which is usually easy, as the substitution m equals to 0 or m equals to 1 usually simplifies the expressions at hand significantly. Then we have to complete the induction step, which only involves proving the statement for n plus 1, assuming that it is true for n, which is again usually easier than proving the statement for n plus 1 without the induction hypothesis. The drawback will become more apparent after the next example. Example 2.2. Let f of m be the maximum number of domains into which m straight lines can divide the plane. Then f of m equals to m times m plus 1 divided by 2, then plus 1. It is clear that one straight line always divides the plane into two domains. So f of 1 equals to 2. And the initial step is complete. The reader can easily verify that the constructions below are optimal for m equals to 2 and m equals to 3, and therefore f of 2 equals to 4 and f of 3 equals to 7. This step is not a necessary part of our induction proof, but it helps the reader visualize the problem. Now let us assume that the statement is true for an integer n, and let us prove that it is true for n plus 1. Let S be one of our n plus 1 straight lines. We may think of S as the straight line we added to our picture last. Then S intersects at most n other straight lines, since there are only n other lines in the picture. Denote by T1, T2, and so on until Tk the straight lines that S crosses, in the order it crosses them in some order. As we said, k is less than or equal to n, since there are n plus 1 lines all together. This means that S passes through k plus 1 different domains formed by the other n lines and cuts each of them into two new domains. Indeed, S cuts through a domain before crossing each Ti and after crossing Tk. In other words, S increases the number of domains by k plus 1, which is less than or equals to n plus 1. Therefore, we have just proved that f of n plus 1 is less than or equals to f of n plus 1, and the equality occurs if and only if S does intersect all the other n lines. Thus, f of n plus 1 equals to f of n plus 1. However, the induction hypothesis claims that f of n equals to n times n plus 1 divided by 2, then plus 1. Therefore, f of n plus 1 equals to f of n plus 1, which is equals to n times n plus 1 divided by 2 plus 1, and plus n plus 1, which is equals to n plus 1 times n plus 2 divided by 2, then plus 1, completing the proof. This proof was possible because we were given a formula for f of m to prove, just as we were given a formula to prove for the sum of squares in the previous example. Had we been not given these formulae beforehand, first we would have had to guess them Then we could have proved them by the method of a mathematical induction. This is the disadvantage of the inductive method we were referring to. However, this guessing is not always hard to do, as the following example shows. Example 2.3, let a0 equals to 1 and let an plus 1 equals to 3 times an plus 1 for all positive integers n which is greater than or equals to 1. Find an explicit formula for f for an. We will learn techniques that enable us to solve problems like this without any guessing. For now, however, let us compute the first few values of the sequence. We get that they are 1, 4, 13, 40, 121. It is easy to conjecture that am equals to 3 to the m minus 1, then divided by 2. Now we are going to prove our statement by induction. For m equals to 1, the statement is trivially true. Now assume that the statement holds for n. Then an plus 1 equals to 3 times an plus 1 equals to 3 times 3n minus 1, then divided by 2, then plus 1, which is equals to 3 to the n plus 1, then minus 1, then divided by 2. So the statement also holds for n plus 1, and the proof follows. Remark, readers should have a basic understanding of the method of mathematical induction by now, and probably noticed that at the end of the induction proofs, we always choose m equals to n. Therefore, we will no longer use different variables for m and n. For our purposes, a finite set is a finite unordered collection of different objects. That is, the set 1, 3, 2 and the set 2, 1, 3 are the same sets because they only differ in the order of their elements. And as we said, sets are unordered structures if an element is allowed to appear more than one time in a collection, such as the element 1 in the collection 1, 1, 2, 3, then that collection is called a multiset. We say that the set B is a subset of the set A, denoted B, which is a subset equals to A, if each element of B is also an element of A. In this case, it is clear that B has at most as many elements as A. In elementary combinatorial enumeration, the most important property of a set is the number of its elements. Usually, if a statement of an enumerative combinatorial nature is true for one set of size n, then it is true for all sets of size n. Therefore, it is permissible and certainly convenient to use one example of an element set for most of our discussion, that the first n positive integers, that is the set 1, 2, 3, and so on until n. As this set will be our canonical example, we introduce the notation n with brace equals to 1, 2, 3 until n, such a set for this set. Theorem 2.4, for all positive integer n, the number of all subsets of n braces is 2 to the n. Proof, for n equals to 1, the statement is true as 1 has two subsets, the empty set and the set contain only one element, 1. Now assume we know the statement for n and prove it for n plus 1. We divide the subsets of n plus 1 braces into two classes. There will be those subsets that do not contain the element n plus 1, and there will be those that do. Those that do not contain n plus 1 are also subsets of n braces. So, by the induction hypothesis, their number is 2 to the n. Those that contain n plus 1 consist of n plus 1 and a subset of n braces. However, That subset of n braces can be any of the 2 to the n subsets of n braces, so the number of these subsets of n plus 1 braces is once more 2 to the n. So altogether, n plus 1 braces has 2 to the n plus 2 to the n equals to 2 to the n plus 1 subsets, and then the theorem is proved. With all its strength, the method of induction can also be dangerous if not applied carefully. One common pitfall is to omit a careful proof of the initial step, then prove a faulty statement by a correct induction step. For example, we could prove the faulty statement that all positive integers of the form 2n plus 1 are divisible by 2 if we could start the induction somewhere, that is, if we could find just one positive integer n for which this property holds. The induction step would be easy to complete as 2 times n plus 1 minus 2n plus 1 will be equals to 2n plus 1 plus 2 minus 2n plus 1, which is equals to 2, is certainly divisible by 2. The initial step, however, cannot be completed. The following provides an example of a much more subtle fallacy. We claim that all horses have the same color. As the number of all horses in the world is certainly finite, we can restate our claim as follows. For any positive integer n, any n horses always have the same color. And here is our proof by induction. For n equals to 1, the statement is obviously true. Any one horse has the same color as itself. Now suppose that the statement is true for n and prove it for n plus 1. Take n plus 1 horses and line them up. Then the first n horses must have the same color, say black, by the induction hypothesis. But the last n horses also must have the same color by the same induction hypothesis. So they too must be black, as we already have seen that all the first n horses were black, and that included the second, the third, fourth, and so on, the nth horses, which are also included among the last n horses. Therefore, all n plus 1 horses are black. It is not so easy to catch the faulty step in this argument because this argument would indeed work for all values of n except for n equals to 1. When, however, we want to apply this argument to prove that the statement holds for 2 horses using the fact that it holds for 1 horse, we encounter insurmountable difficulties. The reason for this is simple. In this case, the first n horses simply means the first horse, while the last n horses means the last horse. These two sets have no intersection, so nothing forces the color of the horse in the first set to be the same as that of the horse in the second one. This fallacy shows that we must be careful that our induction step is correct for all values of n greater than or equal to the value used in the initial step. Of course, our argument shows that if any 2 horses did have the same color, then all horses would have the same color, but that result would be a horse of a different color.